Alright everybody, I'll try to make a little video for you guys right here. My apologies for the format of this. I did want to, I have a paper. I usually make the video with a piece of paper, but I left the paper at school, unfortunately, so we're stuck with my laptop. But I think it'll still be legible, so let's go with it. So to first of all, problem one, you guys hopefully didn't have much trouble with. Write down the augmented coefficient matrix, right? And then we do row reduction, another row reduction. It gets us to this, which is of course 187 is the solution. X equals 1, y equals 8, z equals 7. And so there's not much to say about that. That's pretty cut and dried. I hope everybody got that one. Now this one here might have been a little more troublesome. Here we have two equations and 4 unknowns, and so that gives me a 2 by 4 matrix, coefficient matrix with the augmented coefficient, so it's a 2 by 5. Again, we do row reduction, we get to this, all right, and then from that I read off that the pivot variables can be written in terms of the non-pivot variables and also constants in this case. Then when I plug those into x1 and x2, and of course x3 and x4 are parameters, I should expect that my solution has 4 components, because there's an x1, an x2, an x3, and x4. And when I factor out the x3 and the x4, well, I'm left with this vector and that vector. And what's going on here is that we have part of the solution which fits in the so-called null space, and then the other part is what you'd call a particular solution, right? It actually solves AXP equals to B. Now, if you've had differential equations, that kind of structure might be familiar to you. If you haven't, well, that's okay. All right, so there's that. Now, and I asked for the solution to be in standard vector parametric form. What that means is I'm writing it in terms of, a linear combination of vectors like I did here. And the standard form for us means that I'm using the non-pivotal variables as parameters. That makes the solution more or less unique because the reduced echelon form is unique. So if I write it in this format, there is one right answer. Okay, so moving on here. The next problem, I gave you that the reduced echelon form of V1, V2, V3, and V1 is equal to this. Now, I didn't even tell you what the original V1, V2, and V3 were. Oh, wait a minute. Yes, I did. Huh, that's funny. 86753099999. Huh, interesting. Okay, so then from this reduced echelon form, I can read off. There's a correspondence, right? The fourth column is 1 times the first one, 2 times the second one, 3 times the third one added together. And so by the column correspondence property, that pattern must also be found amongst the original columns, which tells me that B1 is V1 plus 2V2 plus 3V3, and indeed, that bears out to be true. Well, I guess we don't know that's true, but we can figure out what B1 is on the basis of this, is the point, all right? So B1 has to be built from V1, V2, and V3, just like column 4 is built from columns 1, 2, and 3 here by the column correspondence property. Okay, so moving on here. Let's see here. For what choice of C do the lines x minus y equals to 2, x plus y equal to 4, and x plus 2y equal to C have a common point of intersection? So you could either use ad hoc methods where you're just substituting, like I do down here, or a little bit more systematically use the row reduction technique. I start with the 3 by 3, which is 3 equations, 2 unknowns, but we've got an inhomogeneous term. So I row reduce to here, and you can see that if I want to make sure that my last equation isn't 0 equals to 1, I must have that C is equal to 5. So if we have C equals to 5, then 2 of these lines become the same line, and then we have a unique point of intersection. All right? Of course, generally speaking, 3 lines don't meet the point. So, yeah. All right. So as I've mentioned a couple times, well, maybe not a couple times, but at least once in class, we don't know the determinant yet. You can't use the determinant yet. ChatGPT may have told you to use the determinant. I don't know if you're like my son. But we don't know determinant yet, so we can't use it. All right? Anyway, that wouldn't really help you much here, probably. But here we're supposed to find the inverse. This is a pretty cut and dried problem. We take the matrix, we adjoin it to the identity matrix, we row reduce until we get the identity matrix. And having done that, whatever appears according to the algorithm we worked out in class has to be the inverse. And there it is. That's the inverse to A. Of course, you can double check your answer, and you should, by multiplying this matrix by the original matrix and seeing that you get the identity matrix. If it works, it would work, right? So this column, I get times that gives me 1, this times that gives me 0, this times that row gives me 0, this dot product with that gives me 0, this dot product with that gives me -2 plus 5 plus 0, also known as 1, hooray. This dot that gives me 0 because I get 2 minus 2 plus 2, which is 0, all right, and so forth. So you should actually think about multiplying your answer times the original matrix. We can check our answer with the inverse matrix. It doesn't take but a second, and at least you have a chance of hunting down an error if you made one. Because there are, after all, a lot of arithmetic mistakes that can be made here, and I do judge the answer, so you do need to try to be careful. Steps do matter. All right, this is finding the LU decomposition. Here I'm using the super snazzy quick method, so I row reduce, and when I do the row reduction, I put the opposite of the number with a parenthesis, so like row 2 minus row 2 row 1 puts this 2 here, row 3 plus row 3 plus 3 row 1 puts that -3 here. We didn't have a minus in the examples in class by coincidence, but here's an example. Plus here puts a minus there. It's the opposite thing, right? And then to clear out under the 6, I have to subtract -1/2 row 2, which puts a half there. I think at that point I'm done with the forward pass. And from that I can read it off. So I have my upper matrix is this 2, 1, 0, 2, 0, 1, 0, like so. And the lower one is you put 1's dot in the diagonal, and the 2 and the -3.5 there. And the reason for that I explained in terms of explicit elementary matrix multiplication. So if you don't find this method satisfying, you can go back to the elementary matrices and work it out like I did in class. But this, of course, is much faster. But there you go, that's the LU decomposition, which we could solve systems using that, like we did in the homework. All right, so next up, problem 7. I have here 2 vectors, and then the question is, what do we need condition-wise for ABC to be in the span of V1 and V2? And then also, what condition do we need for V1, V2, and ABC to be linearly independent? Now, I will admit, all right, both of these are easily solved with the determinant, but we don't know that yet. So it's good if you know it, but all in good time. For now, we must row reduce. All right, so yeah. So I start with my vector v1, v2, and the hypothetical ABC vector. I row reduce this thing, and it gets me to here. At this point, I see, oh, okay, well, in order for ABC to be in the span, I need that this thing zeroes out. Otherwise, I have an inconsistent equation. So for it to be in span, I certainly need the condition that b plus c minus 7a is equal to 0. On the flip side, in order to be sure that this is not in the span of these two, in other words, to say that this and this column are linearly independent, I need exactly the opposite. I need that b plus c minus 7a is not equal to 0 for part B there, in order to get the linear independence of that set of 3 vectors. All right. Yeah, as I said, soon we'll have to determine it even easier, but We don't have it yet, so let's stop talking about it. Tomorrow. We gotta live in today. All right. Great. So problem 8 is just a standard, like here's a matrix, here's another matrix, calculate the addition and so forth if possible. A plus m we can't do because they've got different sizes. A plus m transpose we can't do because they're both 2 by 3s, so we add them. A times m we can make sense of because we've got a 3 by 2 times a 2 by 3, which gives us a, wait a minute, a 2 by 3 by a 3 by 2, which gives us a 2 by 2. This times that gives me 3 minus 4, which is minus 1. This times that gives me 3 times 3, which is 9. Plus 2 is 11. Minus 4 is 7. 1, 1, 0 gives me 1 plus 0 plus 0, which is 1. This times that gives me 1 times 3, 3. 2 times 1, 2. 3 plus 2 is 5. All right. The next one we can't multiply because you got a 2 by 3 times a 2 by 3. You can't multiply a 2 by 3 by a 2 by 3. They don't have, it's a dimension mismatch. All right. And then, but this one we can do because I've got A, which was this here 2 by 3. So I got a 2 by 3 times this matrix minus a 2 by 3 times this M, which is a 3 by 2. So these are both 2 by 2 matrices actually. And I think we already calculated them actually because I don't know if we did or not. But anyway, I work them out. Here they are. This and that. You subtract them, you get 0. So it just so happens that you can get 0. You can get 0 for lots of different reasons. There's one reason. All right, so there's that. And then next problem, we're going to multiply a 1 by 4 times a 4 by 1. We get a 1 by 1. On the other hand, we're multiplying a 4 by 1 by a 1 by 4. That gives us a 4 by 4. The way you do this kind of multiplication is very simple. You just do 1 times this, and then we do 2 times that, 3 times that, 4 times that. Like that's the way that's done. This is just a dot product. 0 plus 0 plus 3 plus 1, 3. All right, moving on. Let's see here. Problem 10. Oh yes, as I warned you, don't do this the wrong way, I kill you. So here we have a matrix times unknown vector equals to a given pair of constants. So to solve this, we multiply by the inverse matrix. The inverse matrix of 3, 5, 4, 7 is this right here, which happens to be, that's 1, so this happens to be 1 over 1, which is 7 minus 5 minus 4, 3. That's the inverse matrix. Like so, I multiply that by AB, and out pops this, so that's what xy is equal to. I do think that that's like much faster than substitution or row reduction, any of the other methods. I don't think you can really beat 2 by 2 symbolic multiplication for a solution if it's available. It's an important technique to know about for a variety of problems. I use that a lot in a lot of my classes, truth be told. All right, so here is a kind of sneaky problem. There's a lot of different ways to solve this one. What I chose to do was to solve it symbolically to start with. So if I have A inverse B transpose is equal to that, if I multiply this by A on the left on both sides, it gives me B transpose is A times that, which is, well, both of those things are given. I think, yeah, because I got A, and I've got this product, right? So I can do A times that, which gives me this. And so once I know that B transpose is this, I simply have to transpose B, because B transpose transpose is B, so B is the transpose of this, which is that, and there you have it. There's lots of other ways to do that problem, but I think the way I just showed you is probably the fastest. So here, I have A as it was in the previous problem, and we have A transpose 0, 0, A inverse, and I define N to be the inverse of M, and I give it blocks C, D, E, and F, and basically I say find them. And so we multiply. Now, you wouldn't have to do all this necessarily if you just remembered clearly that this is a block diagonal matrix, so the inverse of that block has to be C, and the inverse of this block has to be F, and we know that D and E are 0, but I'll work that out here basically. So I find out that A inverse is this, and that makes D be 0 and E be 0, and on the other hand, the A transpose times C is equal to I, which tells us C is A transpose inverse. So yeah, so that's N is like this, but of course we have the specific matrices, so we can put them down. Something that I should mention that I don't think we ever got around to in class is you can prove that the transpose of the inverse is the inverse of the transpose. So if I've got like A transpose inverse, it's equal to A inverse transpose. That's how it works out. If the matrix is invertible, its transpose is also invertible. It's an inevitability. This here is just a basic find your basis for your column space and null space problem. We did a few of these in class, I think. Column space, we're looking for the pivot columns, which in this case are 1, 3, 1 and 3, which makes columns 1 and 3 of the matrix, your pivot columns, and corresponding the basis for your column space. To find the basis for the null space, you have to do a calculation. We have to look at AX equal to 0, and since we have the reduced to echelon form of A, we can sort through what that means by plugging in the equations for the pivot variables, in this case x1 and x3, in for x1 and x3. And we simply use the non-pivotal variables as parameters in our solution. In this case, x2, x4, and x5. Now those factor out, like so, and what's left have to be the basis for the null space. All right, that's the way that works. We should always have the case that the dimension of the null space, which here is 3, plus the dimension of the column space, which here is 2, has to equal the number of columns in the matrix. The dimension of the null space we called nullity. The dimension of the column space we called rank. This is sometimes referred to as the rank nullity theorem, that the sum of the rank plus the nullity of a matrix must work out to the number of columns. This here, I think we had in homework, or I worked it in class, I don't know. Standard calculation, the trace is this, but then matrix multiplication gives you that. Swap the orders of the sum, use that use the numbers commute, and then undo the steps by undoing the matrix multiplication in the opposite order and identifying that you get the trace of BA. So there's a few different problems like that to think about for the test. This is one of them. Another one I oftentimes ask is proving the sock shoes property for transpose. That's a good problem for you guys. Or I guess possibly like proving A times B plus C is AB plus AC. Pretty much those, if you can work those 3 problems, you're good to go. I think everything I just said either worked in class or was a homework problem. Now this here, the point of this problem, this one probably might, I think I probably got some of you guys on this one. It's actually not that hard, but you have to understand it. It's a little bit tricky because I'm using E1 in 2 different ways. E1 here is a 3 vector, because A times E1 is that, which makes this whatever A is times, it forces the number of components in E1 to be 3, since the output's 3 vector here. So that tells us that A has 3 rows. On the flip side, this means row 2 of A is that. This one here is a little bit trickier, because this tells me that actually the number of columns of A, well, this also told me the number of columns of A is 5. But this here, if we transpose this equation, I get, by sock shoes, E1 transpose A transpose transpose, which is to say E1 transpose A, which of course is row 1 of A, is 1, 2, 3, 4, 5. Okay, so then we're given that the rank is 1. What that means is that every column must be basically a scalar multiple of the other one. But the same has to actually be true for rows if you think about it. So if I have that every row is just a scalar multiple of the other, then that forces the third one to be 3, 6, 9, 12, 15 in this situation, because it has to just be a multiple of the first two. If the third row was not just a multiple of the first two, then the rank wouldn't be 1, it'd be something else, all right? So, a little bit tricky, but there it is. This one here, one of the things you really should know to safeguard against my plans against you, to safeguard against my scheming, to protect yourself from my many, you know, evil attacks on your grade, however you want to look at it. But so beware of the fact that the antisymmetric matrix has to have zeros down the diagonal, because A11 has to be equal to minus A11, A22 has to be minus A22, A33 has to be minus A33, A44 has to be minus A44. The only way we can do that with real numbers is to have the diagonals exactly 0, all right? Because they have to be equal to minus themselves, which forces these to be 0. And then I also told you the off-diagonal upper elements were 86, 7, 5, 3, 0, 9, 1, 3, 1, 4, 2, 3 is 3, 2, 4 is 0, 3, 4 is 9, and once you have that, then the antisymmetry immediately fills in the rest of it down here like that, all right? So that's an antisymmetric matrix. Yeah, we talked about it a little bit before, but there are some nice antisymmetric symmetric matrix problems that you might see on the test. So make sure you know what symmetric and antisymmetric means, and be ready to work some just basic matrix identity problems about those, perhaps. It's a good place for me to ask a symbolic question of you guys. All right, moving on. 17, again, a kind of a little bit of a challenge question for you guys here, but it's pretty simple actually if you just look at it this way. The identity matrix is this matrix plus that matrix plus that matrix. In the notation in my notes, which I may not have used in class much yet, that's E11, this is big E22, this is big E33. I just can't remember, guys, if I ever did that in class or not, and part of the reason I'm putting this problem here is to make sure we all see it before the test, because it sometimes comes up, all right? But anyway, so these are the unit matrices, as I call them. And we can build unit matrices from the product of a matrix times its transpose. Like to get E11, we do E1, E1 transpose, E2, E2 transpose, E3, E3 transpose. So that was the answer here. And there's really no shame if you didn't see that. I'm giving you this problem on the practice test to try to draw your attention to this mathematics. You might not have noticed it before. It might not have been emphasized in my homework before this point. Okay, that's part of the thing I do with this quiz, is I try to make sure I fill any I perceive as a gap in the homework as I currently have given to you guys, all right? I would classify problem 17 kind of in that mold. And problem 18 is perhaps interesting. I think this is, I do want you guys to be ready for like a question about a span or linear independence, and I think this hits on some of those things, and also basis. Remember, basis is a linearly independent spanning set for the set in question. So we've talked about how to find the basis for column space, for null space, but we can also talk about finding the basis for other things. Again, the basis just has to be a set which the span is the whole thing, and it has to be linearly independent. So here I give vectors v1, v2, v3, v4, and v5, and I tell you that the row reduction of these guys is this, all right? So is v4 in the span of v1, v2, v3? Well, we could look at this, and see that the fourth one is 3 times the first, plus 1 times the second, plus 1 times the third. So by the column correspondence property, we find that yes, it is in the span. In particular, v4 is 3v1 plus the v2 plus v3. And of course, you can check that that's actually the case, all right? So, point of order here, if you're doing any calculations to figure that out, you're doing this wrong. You shouldn't have to solve a system or anything here. You should understand the column correspondence property and let it do the work, all right? Now, I'm not saying necessarily that every problem in the test is not going to have any work. in the sense of like on the test I might actually, probably will, at least for a couple problems, I would expect that the test has at least, I don't know, 20 row reductions, something like that. There should be a significant number of row reductions on the test. But I try to make a mix of things where I have one problem where I give you the row reduction so I can test your understanding of what to do with the row reduced echelon form of the matrix as opposed to calculating it. There's two very separate things, interpretation and calculation. They're both important. But anyway, so this is more about interpretation as opposed to calculation, right? Okay, so moving on here, if I can straighten out my laptop, we have part B is V5 in the span. I guess I have to go back up. Maybe shrink it down a bit here. Whoop. Boop, boop, boop. All right, so no, V5 is not in the span because the fifth column here is clearly not a linear combination of the first three columns, right? And so since this is not linearly dependent on those, neither is V5 linearly dependent on those. That's, again, by the column correspondence property. If there was to be a linear dependence among V5 and V1, V2, V3, that would imply that there's also a linear dependence between this first three columns and the fifth, which there is manifestly not. All right. Okay, so that's the answer to part B. For part C, find a basis for the set of all five vectors. So there we simply use the column vectors, the columns here, first one, second one, third one, and fifth one. Those are linearly independent. All right, because these ones are the pivot columns, which are linearly independent. All right, so that's what we could use for the basis. Basically, just throw 4 out of there. You don't need that for the basis because we already got it building. We can already build 4 with the other 4. So that's how I do that. Now, are there other choices of bases? Sure, probably I could use like 1, 2. I probably could use like 1, 2, 4, and 5. That probably would also work, but you know, I'm not asking for what are all possible bases. I was really hoping that you give me the laziest possible choice, which is simply to use the pivot columns, which we know are linearly independent. The question of what are all other possible linearly independent choices amongst the 5 columns is a much more complicated question that I think I could describe how to answer with, well, determinants. We don't know what those are, so I'll stop. Find a basis for the perp of V1, V2, V3. Now this is probably maybe the toughest thing on the test, just in terms of the fact that we haven't spent a lot of airtime on this yet, but I have mentioned the idea a couple places in class. And here's what you do. You're looking for vectors which are perpendicular to V1, V2, and V3. So what that means is you want to find the null space of the transpose. So actually you lay the vectors flat like this, row reduce, and when you do, you get this. And from that you can read that x1 is minus x2 plus minus x3, and that x4 is 0 and x5 is 0, which gives us that the null space is actually two-dimensional with parameters x2 and x3. And these are the vectors minus 1, 1, 0, 0, 0, and minus 1, 0, 1, 0, 0. These two vectors are, you can easily check this, that both of these vectors are perpendicular. If you take the dot products of this and this with these 3 guys, you get 0, which shows you that I did the calculation right, all right? And there's a pattern to be seen here. If you're looking for the perp of 3 linearly independent vectors in a 5-dimensional context, it will always be the case that the perpendicular space is 2-dimensional. The sum of the dimensions of like the subspace and its orthogonal complement, or its perp if you like, they always have to like add to the total dimension. So like if I have a line in 3 dimensions, then the space which is perpendicular to it has to be a plane, because you need like 2 plus 1 is 3. If I have a plane in 4 dimensions and I want to find the space which is perpendicular to a plane, it's got to be another plane, because 2 plus 2 is 4. If I have a line in 2 dimensions, its perp is another line, because 1 plus 1 is 2. That's the pattern. Anyway, my voice is starting to go, so I'm going to have to stop here, guys. Finally, the angle between V1 and V2, we just use this definition of angle, which is the dot product of V1 and V2, divided by the magnitude of the lengths, which in this case, if I haven't made a silly mistake, it works out the inverse cosine of 7 over square root of 5, square root of 11. The square root of 5 and square root of 11 are, let these not be mysterious. The length of V1 is square root of 5, because 1 squared plus 1 squared plus 1 squared plus 1 squared plus 1 squared is 5. Square root of 5 is its length. And I think V2 was 1 squared plus 1 squared plus 1 squared, which is 3, plus 2 squared, which is 4. 3 plus 4 is 11, 7 rather, and 7 plus another 2 squared is 4, so that's 4 plus 4 plus 1 plus 1 plus 1. 8, the square root of, my bad, it's 11. The square root of 11 should be the magnitude of V2. I think that's what I had down here. Yeah. And the dot product of V1 and 2, let that also not be mysterious. We're just doing 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 2 plus 1 times 2, which is 1 plus 1 plus 1, which is 3, plus 2 is 5, plus 2 is 7, right? So the dot product of V1 and V2 was 7. So we have 7 over those square roots, the inverse cosine of that thing, I get 19.29 degrees. So some of you asked me, a couple of you asked me, it's like, how long is the test? Which of course is a reasonable question to ask, but somewhat meaningless. Because the answer, of course, is always that the test is long enough, or too long if you don't understand. But this quiz is definitely longer than the test. What I will try to do, of course, is to construct a test which is probably more like, probably more like 5 pages, maybe 6. So, I mean, there'll be a lot to do, right? But not quite as much as this. So anyway, that's my intention. Now, are we going to have a test on Wednesday? Well, that's anybody's guess. Like some of my colleagues, and we're a little bit like, we've canceled classes before there's an ounce of snow on the ground. You know, there's a drop of precipitation here, which is kind of like, we'll see what happens. But it's anybody's guess, obviously. If there's a ton of snow, you know, we're not going to have the test Wednesday, so fret not. I'll just hopefully just push the test to Friday. And what I would do is I would just record a lecture on determinants and post that with the hope that you would not watch the lecture, I guess, because I don't want you to use determinants. I really don't want it to snow on Wednesday because it doesn't help us in the big scheme of things. But anyway, I think that's it for now, guys. Thanks.